repeating part of what we talked about the last couple of minutes yesterday. So this later I can take away. So first, a couple of general words on the cotangent vectors on a manifold. I'm just briefly repeating something I said yesterday. If we have a manifold, I suggested that we avoid thinking of the cotangent vector as a vector lying in the same space as the points x. Instead, by definition, the cotangent vector is a linear form on the tangent space. And since the length of the cotangent vector is irrelevant, the up to plus minus at least, the cotangent vector is uniquely determined by the space of all tangent vector, which is annihilates. That is, it's zero space, which is a hyperplane through the origin in the tangent space. And again, if we are talking about a vector space like Rn, then we can specify a hyperplane through the origin in the tangent space at the point by actually giving a hyperplane through the point in the space itself. But if we are living on a manifold, planes in the manifold don't make sense. But we need to specify only a hyperplane in the tangent space, and that is given by any surface, piece of a hypersurface through the point in the manifold. Obviously, any two such hypersurfaces that are tangent to each other at the point, they determine the same subspace, codimension 1 subspace of the tangent space. That the set of all little tangent vectors at the point through any of the surfaces. And now, in the case of the manifold is a set which we call Y yesterday, called set of all hyperplanes in Rn. This is our manifold now. Then I suggested to specify such pieces of hypersurfaces by giving a point in Rn and defining something I will denote by gamma sub x0, which is going to be one of those pieces of hypersurfaces. No. Well, it was wrong to denote this by x0. I should have denoted it by y0. This is the manifold. I denoted my lines by y yesterday. So here is the x space, and this is now the y space. The elements are hyperplanes now. Yesterday there were lines all the time, but what I'm now saying is even more instructive to think of planes, hyperplanes. So this is R. And so what is that piece of hypersurface? It is the set of planes, hyperplanes in Y that contain that hyperplane. And I'm saying, since it's a hypersurface, again, up to plus minus, the cotangent vector is determined by it. Again, yeah. So, let me repeat also the correspondence, which was between, let's have x 0, c0 here. These are elements in t star x, where x is Rn, and points y0, eta 0 in t star y. Where these now are hyperplanes and these are cotangent vectors. And the correspondence is, as I explained yesterday, actually defined by the wavefront set of the Schwartz kernel of the Radon transform. What is the correspondence? Well, I start with such a pair. I'm going to tell you what this pair is. Well, if here we have the point and we have the C0, which lives in another space. Now the plane, the point here, which is a hyperplane, is going to be the hyperplane which is perpendicular to that cotangent vector. So we've got this, and what is that going to be? Well, now I denote it by L sub 0, which is the same as 1. Well, it is the cotangent vector which is conormal to that piece of hypersurface, which is specified by the point. So again, geometrically, we have a hyperplane, that hyperplane, and that is given a point, and then we allow all little wigglings around of L, all movements while the point still stays on the hyperplane. This is a hypersurface in the space. Why? Because it's the fact that the point is on the plane is given by one equation. So this is a correspondence. So just one remark again about the fact that these are not directions in the X space. But already when we talk about the Fourier transform, we don't need the inner product in Rn or when we define the Fourier transform and deal with the Fourier transform. So the little dot here should not be thought of as an inner product dot, but the C's are if X are in an arbitrary finite dimensional vector space, and the C's are in the dual of that, that's the way we should think of the Fourier transform. So already for that reason, the elements, cotangent vectors, are not to be thought of as directions. And one final remark, actually the terminology wavefront set is very intuitive, because especially if you want to pay attention to the difference between plus and minus, then these little infinitesimal hypersurfaces or hyperplanes should be oriented. So if we have such a little infinitesimal piece of a hypersurface through the point which is also oriented. It's very intuitive to think of it as a wavefront. So that's another comment. But now, I decided, while preparing these talks, I made little drawings for myself, which I wasn't sure whether to show you, but since there was some, I think this is an interesting point, there were some questions yesterday, I decided to show you. I hope you will find it illuminating and even, fun. As I do. So let's take the Radon transform with the chord. Now we are back to 2 dimensions. And I'm going to use the coordinates as I did yesterday, or f y is equal to integral fx1 y1 x1 plus y2. So y1 is the direction of the line and y2 the vertical position. So I decided to choose f as a characteristic function of this is the common notation for characteristic function. So it's 1 here, 0 here. I want to actually draw the function g y here. So it's the function of y1 and y2. What? Why? It is rather. I can't draw the values of the function, but I will draw the support. So this is y1, y2. The reason I do it is that I think it will help to clarify the relevance of this cotangent vectors eta. Well, if I should have the formula here. X1, y1, x1 plus. So if y2 is 0, then this means just integrating along a line like that. And the integral will obviously be 0 below y1 minus 1 and 0 up here. But now if y1 is 0. Yeah, perhaps I said that. But if y1 is possible, which means that the line has a slope, then the y interval of y2 for which the result will be different from 0 is slightly larger, as you can see. This means that the boundary of the support will be curved like that. So I decided, this Radon transform G will be non-zero in between those curves and 0 up here. And also, obviously, it will be smooth in the upper region between. For instance, on this curve, we can compute it. The 0 y2 is the length of such a corridor. So I think it's twice 1 minus y2 squared. Please correct me if I'm doing something wrong. So you see, there's singularities here at the boundary point, but not 0 upwards. So the behavior will be similar everywhere. It will be something similar. So now I decided to choose a point. I must change this a little bit. Point x 0 equal to minus 1/2 square root 3 is this point. F I chose on the boundary because that's still where F has singular jumps. Now, let's take a priori the Radon transform G might have a singularity if the line meets a point where it's a singularity. But according to our analysis and according to the example, this won't happen unless the line is tangent to the boundary, which means, what this point, this line corresponds to y2 equals 0 and x1 and y1 equals 1/2. It's somewhere here. And we are, in the region where the Radon transform is smooth. But now, let us compute, now comes the fun thing, let us compute, study the set of all lines through that point. Why the relationship between a line and a point is like this. So if I put in those values of x, I get y2 equal to plus 1/2 y1 plus x this. So it's the slope should be 1/2 so this point corresponds to the tangent line here. So, and we can see in the picture that the Radon transform has its singularity here. And as it should, according to this theory, since the line is conormal, perpendicular to C zero. But remember, we had Rakesh's question in the last minute, where he asked, having heard this explanation, what the eta zero is, he said something. What does it say about the singularity? Or perhaps he meant even more brutally, why should I know this? I don't know. But here is the answer. It says, in this case, that is, it says what the nature of the singularity is, namely that either it has a jump or it has this, along that piece of hypersurface that I've been talking about. That hypersurface, that gamma, this hypersurface is this curve. In this case, the curve, something wrong?
No, a quick question. So the singularities can be detected if and only if the Radon transform is taken along a line that is perpendicular to the object. Is that what you're saying?
Yes. No, I'm not talking about can be detected. I'm talking about the more trivial, the forward thing now. But I'm talking about which singularities in the object will show up as singularities in the Radon transform itself. This is called the sinogram. But it looks weird because I'm using these coordinates. But since the relationship is reciprocal, so the relationship is the same, but going back. So we learn about what you are asking equally well from this. not a good answer. But anyway, the answer to Raquel's question is that the singularity at that point is its kind is determined by this eta vector, in the sense that it may not actually be a jump, discontinuity, but in this case it's weak, but it has the same kind. Namely, it's not even it's a little worse than a jump in the derivative along that curve. That's what we learned. So let's what's your question? Concerning your question, what we learn from this is it's precisely because of this relationship, precisely this part of the Radon transform, that is the set of lines close to the tangent, which give us information about this singularity here. The other lines which are not perpendicular don't see this singularity. Okay. So I thought this was thanks. There is, in fact, one can play with this such figures more. But in this case, there was just one. There's, according to the theorem, there's a one-one relationship between the pairs x, c, and y eta, but in this case there was also a one-one relationship between the points because of the nature of the f. But if I choose, it's fun to compute. I'm not going to do the detail. To compute, choose f with a singularity at, say, the origin with all cotangent vectors about that point in the wavefront set. And the easiest example is the delta function. And how do you compute this if f is a delta function priori? Well, you need to set up a duality. If I define by duality R f p equal to f R, that's what we always do. We need to define the pairings here. These objects are functions of y. So let me define this as by C G X by
This could be y? I mean,
yes, dy1, dy2.
no, I mean,
Yes,
y coordinates for.
No, x. This was x. Thank you. Okay. This is for y, and the same for x. Then the r star becomes, this formula becomes valid with r star, define r star phi, say, phi y1 minus, with a little minus sign, but everything else is zero. So x1 and x2 now determine which line. And then, using this definition, the Radon transform of the delta function at the origin will become, well, I can draw it here. A measure all along the spread out with mass at the x1 axis, the y1 axis. So then where that set will consist of such conormals. So to any direction here with any wave set here sitting at the same point will consist will correspond different that way. So now let us leave that to move on. Are there questions on this? I didn't prove anything. Just a couple of words about it. In the case of lines, this inclusion first. The little prime, denotes well, we choose suitable points. It's a joke. What does it mean? It means if a certain element y0, eta 0 is not in here, the corresponding x0, c0 must not be in the wave conservation. Yes. So I'm going to choose coordinates so that both elements will be. Let me write amounts to prove uniform. If 0, 0, 0, 1 is not in the wavefront set of F, then the same point is not in the wavefront set of G. Why take an arbitrary.
G is RF, right?
Something.
G is RF.
D.
G is RF.
Yes. Yes. Fine. Yes. Well, I chose coordinates. Let x see an arbitrary point. I choose coordinates such that x0 is the origin, and then I rotate so that this vector points upward. But and moreover, then I claim that. So I've achieved. I can assume x0 is, although c0 is 0. But then, by choosing coordinates, then because of the correspondence, y0 and eta 0 must be the same, at least up to plus minus. I don't have these equations in front of me now, but they follow from the equations I wrote down yesterday. And also from the geometric considerations we are doing. So therefore, this is what we have to prove. And I did very brief on this. Just I'd like to show what's involved. Yeah, let me repeat here. G, Y. Well, I'm going to get the proof of this from the definition. Well, first of all, I claim that what takes place, that parts of F away from the origin can be disregarded, because let's assume for a moment, actually to be precise, I'm going to chop up F in two parts by choosing function phi with very x1 with small support and equal to 1 close to the origin, and write f phi plus f plus f1 minus phi. So this part is 0 in the neighborhood of near the origin. I claim that this part cannot contribute to wavefront of G near at the origin, because if you look at this as a function of y for a fixed x1, if x1 is different from 0, it's of the kind that we talked about a lot earlier, namely function of the type a which is constant on lines in the y plane. And if this a is different, say x1 is different from 0, these lines have a slope different from 0, which means that the cotangent vectors must be different from the one we want to prove is not in the wavefront set. So we can throw away that part and consider just this one. And then we are near the origin. I will write just one formula. We want to prove that a certain element is not in the wavefront set of G, then we have to multiply it by the capital function and take full transform. And I choose C, let's call it Y as a product, as I did times before. And then begin and take full transform. And again, we'll begin with eta 2. So I form integral function eta y eta 2 psi y2. Of course, later I will iterate with respect to the good y1 also, but I tell you after trivial computation, just one or two lines, this becomes e to the minus y eta 2 x 2 minus side x2 I'm sorry, I have to continue here. Phi y1, no, phi x1. F x1 x2 x1. What I've done, I made a translation in variable and I've changed name of the one of the variables. So we have dx1 in the definition and the y2 here, which I just changed name to.
What is paradox 1? How to build here?
Oh, it's this here. I chopped off it to get rid of the rest. So we need now just look at this exponent here. I write this exponent eta 2 as a dot product. 1 minus y1 dot. Oh, I should have it the other way around. Minus y1 comma 1. Now, if we have, in the next step, I will multiply by psi y1 with respect to y1. And I can choose the support of this as small as I like, close to the origin. This means that y1 occurring here will be close to 0. So this plays the role of the. So this, well, it doesn't matter. Anyway, what is it? It's essentially f multiplied by the smooth function evaluated. Let's call it phi, this whole bunch of things. It depends on y1, it doesn't matter. This is equal to full transform of evaluated as y2 minus y1. 1. So if we have chosen this with sufficient small support, these directions will be close to the vertical axis, where we have assumed that F has no wave transfer. So we by assumption about F, this will tend to zero rapidly when eta tends to infinity. I omitted the trivial details. So this proves one direction. The other direction, in the case of the Radon transform, follows from the inversion formula. And there is an R star there, which, let's see where I can take away this. Maybe I write down. Well, inversion formula for the Radon transform. There are many ways to write. F is equal to some in 2 dimensions. Square root of Laplacian and R star R. And this is actually a convolution with a distribution. And we'll see in a couple of it's easy, it follows from general fact and also from things that I will talk about in a couple of minutes, that this convolution operator is smooth outside the orbit, and therefore it doesn't add anything to the wave transfer. For F in U. So apply this fact to this thing here. So therefore, the only pieces that remain to understand that the other inclusion is also true is to understand that this fact and the fact that R star is forward mapping of singularities, thus in principle the same as R. But looking at this, using the coordinates I've been doing, I told you that, wrote even down somewhere, that R star is of precisely the same form, except the little minus sign there. So it's easy to understand that there is the same inclusion for R star as one we've been discussing for R. So, therefore, we have equality. In the remaining minutes, tomorrow, I want to speak about the analytic wavefront set. So, in the remaining minutes today, I would like to explain why what we have been doing for the Radon transform is a special case of something much, much more general, which makes it what we have been discussing more interesting. I'm going to discuss now general linear influence operators of the kind K script KF. distribution on the product space. First of all, I have to, you must excuse now that I'm shifting the notation. So this maps from the function defined on y into the function defined on, depending on x. That's because this notation is always used. And I cannot begin to write yx instead of xy. So if k is any distribution in D prime, what x cross y, we can think of x and y as copies of Rn right now. Then this case certainly maps C infinity into D prime, which is not very interesting. Why is that? Because Kf, to explain what Kf is as a distribution, we have to explain what it does, how it maps to a test function. No, yes, that's right. And yes, what does it do? Well, f is also assumed to be a test function. So with easy to understand but slightly informal notation, yes, the product of f as a function of y and phi as a function of x is a test function in the product space, and that distribution has a value. So this explains this. But it's not very interesting, not very useful. So we need to make assumptions on this distribution so that it maps, for instance, compactly supported distribution to a distribution. And we begin by making assumptions so that it maps. Let me write this way, K. I would like to make assumptions so that this becomes true. And it's very easy to look up examples where it's not true, and these obvious examples also give an indication what we need to assume to avoid it. Namely, suppose K X, the short kernel is product of some function of y and a distribution, for instance, a delta distribution in x. Then obviously the result of such an operation will always be some number times the delta. And also, if we shift here, it certainly does not operate on arbitrary distributions, because distributions of y cannot be matched up like this. And now, back to this. What is the wavefront set of this? It contains certainly we don't know anything about age, so we don't know about the y and eta, but it will certainly contain a lot of well, for all C. No, wait a minute. is not right. That is not right. Let's say that this is for simplicity. What I would like to say is that it contains, because this distribution contains singularities spread out on the y-axis, but concentrated to the y space. So there would be lots of wavefronts like that.
When on the support of y.
Pardon? Yes.
It's not any y.
Yeah, yes.
Y is
Yeah,
y.
right. So here is a proposition. Assume no element of the form x, y, c, 0. Then this has k maps compacted smooth functions and smooth functions. I think I can say this is already an interesting fact, and it's better to write on the other wall. Well, I just need to write one formula and wave my hands a little bit. So, I take Fourier transform with respect to x, and then I choose a generalized Parseval formula with respect to y. So it becomes this double Fourier transform. The minus sign, there is such a minus sign in the generalized Parseval formula. And this is the minus, I have to put it either here or here. I prefer to put it here. And that is the reason why I had to have this prime in the relationship.
You mean k hat? Or now Fourier transform from
both variables.
Yeah, so the right hand side is not k hat.
Good. So I need to show that this always, after cutoff and so, tends to 0. Past c tends to infinity. And I do the usual splitting. Eta less than epsilon c plus eta greater than epsilon c. And now I need to use the assumption. What is the assumption? The assumption is that after cutting off, but to avoid writing, I assume that I've already cut off. So the assumption implies something. For delta. So this condition restricts the C eta variable in the product space to a conic neighborhood of all the vertical elements that are forbidden in the wavefront set of K. Did the assumption disappear? C or not in the wavefront set. I mean X, Y. So directions with eta 0 are not in the wavefront set by assumption. So, and this is a neighborhood of those. Now, it's obvious what to do. We choose delta smaller than epsilon, and then this part we can estimate f hat by supremum, and we can estimate that by this, and as because of this, it will tend to zero past. And for that, we don't need to worry about k hat, because f hat is a smooth function by assumption. So in this really simple case, when k is an L1 function, it's already done, because then this is bounded by a constant. But with a little extra work, which is trivial, you can require a few powers extra decay of f hat. It will take care of some polynomial growth of this. So this concludes the proof. So I by this I will finish today. I had planned, also I talked a little too long about these examples because I enjoy these examples. I hope you did to some extent also. So I had planned the next theorem, which requires slightly more work, but depends on the same kinds of argument, would give the same estimate as we had for the Radon transform for the wavefront set. But perhaps a couple of words about that. Anyway, it's time to